A couple of years later, Tim had left the Institute of Oceanographic Sciences, and I was asked to take up the role of lead engineer on the Doppler profiler work. I gave up on the ship profiler, not knowing what the ship was doing. It's a big problem, and I decided that the easiest thing to do was to build a self-contained instrument that would fit on a frame and sit on the seabed where its motion was zero. And by 1984, I performed my own design, rather limited in its specification. So operating at 1 megahertz, this instrument had 10 2-meter depth cells and a ping only once every 10 seconds. But in the Irish Sea, in May '95, this deployment I was incredibly proud of at the time, and I guess I still am. So what we see is the east component of current with all 10 cells plotted in different colors, and what we see over this time period of 3.5 days is part of the spring into neap tidal cycle at this location. And then we also see by the spread of the amplitude of each depth cell a change in the current amplitude with depth. And in this little graph at the top right-hand side, we see depth over the water depth, going from 0 up to 1, which is the sea surface, and the individual results plotted here against a form of current profile from an analytical model. So this was incredibly encouraging work that the essence of this Doppler profiler that I designed and built on the autocorrelation principle, similar to that from Rowan Dines, could be built and could work in these shallow waters. But as well as the engineering, we were attracted by the possibility of using Doppler profilers in other configurations, not just on the seabed. But here's an example from later in 1985 where I put the Doppler profiler into a tube. This is now upside down. The transducers are up here on a gimbal and looking up towards the sea surface, trying to make current profile measurements in the upper 15 meters of the water column in an area where the tidal currents were rather different, far more chaotic, if you like, than at the earlier site. And then to make a comparison of the low-pass filtered currents between this Doppler profiler, which is in A, for the Doppler cell at 3.4 meters below the surface, with the low-pass filtered current record from a surface buoy measuring 1 meter below the sea surface. So there's a depth difference here of 2.4 meters between these measurements. And in this low-pass filtered current vectors, we are looking at some broad indications of similarity, but certainly not exactly the same. But still, that wasn't too bad. But then, even as an engineer, I started to delve into, well, what were the differences between these two? And by looking at the vector current difference in C here, and then relating that to the wind speed and direction near the site, we can see a remarkable coincidence. And so what the Doppler profiler and current meter at 1 meter below the sea surface are seeing is a wind-induced shear between those two depths. And certainly this gave even more confidence in the Doppler current profiler. Technology was moving quite rapidly over those years, and by summer 1986 I developed a Mark II version, which was in a much smaller pressure housing and could be fitted within a buoy to look down from the sea surface. I'd also given up on the sea data cassette tape data logger and designed and built a solid-state data logger, which had a controller and 2 megabyte cards. And the cost of the EEPROM chips at that time was about $1,000 per megabyte in chips alone. So that equates to about $1 million per gigabyte. So my, haven't things changed in the cost of solid-state data storage. So here we have on this surface following buoy in black here, these are the acoustic transducers, not too easy to see, but at a depth of about 70 centimeters below the sea surface. And then here's an electromagnetic current meter. And on this record, I also started to look at the acoustic backscatter signal within the upper ocean. So here's a rather dull photograph now of my crayon-colored contoured diagram from 1986. So not quite the era yet of color printers that could do color contouring. So what we have up here is the 5 meters depth, and the instrument is looking down 10, 15, 20 meters depth here. And these areas of red are periods of high backscatter caused by bubble injection from the near surface during high winds. And here's another such period towards the end of the record. And we were able to show that you could make estimates of eddy diffusion in the upper ocean based on the decay of the bubble penetration with depth. But there's also an intriguing signal here, that there's a daily variation between the light blue and the darker blue. Somewhat sporadic at the start of the record, but then it really does set in the second half. And the question that then came to mind with my biological colleagues was, well, was this a signal from scattering from zooplankton that had increased in number after these early storms had mixed up nutrients from the seabed? So I soon realized that although you're making a physical measurements of current with the Doppler profiler, it actually lets you ask many more questions about what's going on in the oceanography, and you wished you'd had the instruments to be able to answer them all.